Nice. Okay, well, welcome back. We're picking up on page 1-10 of the book. And here we're talking a little bit about some of what the relational model is trying to accomplish. So we're talking about some of the components of the relational database management system. We're going to shift gears a little bit here and talk about relational design and what it's trying to accomplish. And the relational model is trying to accomplish at least these three things, probably some others. But number one, maintaining the structure of our data. And if you think about some of the other pre-relational ways of storing data, the structure of that data was dependent on the application understanding it. And that's still true if you take your Java object and you externalize that directly into a large object, which is what you guys do at least some of the time here, then you're dependent on the application that reads that data being a Java application and understanding how to map that back into the class that it goes with. And very efficient way of dealing with data, but not always very flexible. And again, relational database theory is all about trying to get flexible access to the data. So one of the things that it's going to try and maintain is structure. And we said the structure of the data is maintained in that relational catalog inside a series of tables with columns and rows. So if I want to see what tables I have out there, I can go out to the catalog and write a query and show me a list of tables. If I want to see what columns are on those tables, I can query the catalog. If I want to see what indexes there are. All of that information is in the relational catalog. So the database engine itself is maintaining the structure, and I don't need to be intimately aware of what goes on in the underlying files. Right, and that's very different by platform. So the way DB2 stores data in the actual physical underlying files will be very different from the way Oracle stores data in the underlying file. And I don't even need to be aware of those differences. I can write SQL, which is a layer, way above all of those internals, to access the data, and I can access it from a DB2 database or an Oracle or SQL Server database in a relatively similar way without being aware of how that data is physically structured on pages and in blocks and where the rows begin and end and all of that. So gaining control of that structure and making it reusable, right, or publishing it in a way that's pretty easy to understand was one goal of relational theory. And if you think about what that's done for us, it's taken data access from a thing that really required developers. When I worked on the systems that used VCNF, which is mainframe random file access, and flat file data, when an analyst needed a piece of data out of a file, they had to enlist the help of a programmer to write a small program to access the data for them. So we've taken it from there to a pretty flexible language called SQL that's pretty easy to understand. And I fairly routinely now will get a room full of business analysts wanting to take an SQL class because SQL is easy enough for pretty much anyone to write. And the thing that allows us to do that is by keeping that structure in a centralized place that's easily accessible. Another goal of relational database theory is to maintain the integrity of the data. And we talk about integrity on a bunch of different levels. So we'll actually have a few slides here coming up that reference that integrity in a bunch of different ways, but kind of making sure that the data makes sense. Right? So one way that the database can help me enforce integrity is by allowing me to enforce the domain of a column. What are the allowable sets of values for this column? Part of that is in a data type, right? When you say it's integer data or it's character data. And when I put a value in there, the DB2 or Oracle or SQL Server is going to make sure that that data makes sense. It meets my domain, set of allowable values. And if you think about that, that's a difference from the pre-relational days too, where I could put anything I want in the file and then I would get errors trying to interpret it if it was wrong. So the database won't allow me to put anything in a column that's not consistent with that column's definition, as defined by DBA. It also allows for this easy manipulation, and that manipulation is what we do in the layer when we write SQL. So again, SQL is fairly simple. It can be simple anyway. Interface to the data that's pretty easily understood by developers and people like business analysts who can query the data directly now without the help of a developer. Whether they write good SQL or not is, of course, another issue. And we'll spend a little bit of time this week talking about what is good SQL. How can I write a query in a way that's easy for the database to understand as opposed to difficult for the database to understand and optimize. Okay. So to get started, let's talk a little bit of terminology. So you'll see some of this terminology kicked around in relational database theory anyway. Back in the old days, they called tables relations. Relation was the term that Dr. Codd used when he described a table. We find that relational theory is actually rooted in math theory. So you see a lot of math words creeping away into relational database discussions. So, Dr. Codd talked about relations and tuples. We call those tables and rows. Okay, so kind of the more common terminology usually is on the right, and then the academic terminology is on the left. I don't ever hear anybody refer to tuples anymore. It's a row, a coherent group of things that go together on a table. Data analysts still sometimes call columns attributes. So, we think of a table as a thing, that we're going to keep track of, right? A business object that we're going to keep track of. The attributes of that table are the things that we're keeping track of, right? The columns on that table. Some of these other words you will hear even today. Primary and foreign keys, very common terminology, especially primary keys. And a primary key is a column or group of columns on a table that will uniquely identify the row. A foreign key is when we take the primary key of a table and put it on another table to establish a relationship. And that's a pretty key concept in relational theory, that the relationships between tables are not established by internal pointers or anything like that. They're established by keys, by the keys to that data that the business would use. And so the way I establish a relationship between two tables, put anything under the covers, is by taking the primary key of one of the tables and putting it on the other table as a foreign key. We can do that, and that's how we usually facilitate joining tables together, is by primary foreign key relationships. We can optionally tell the database about that relationship and not allow it to maintain the integrity of the relationship. Now, I'm told we don't do that here, right? We don't do system managed or declarative referential integrity, fancy words for telling the database about this stuff. Okay, but we can optionally do that, and we'll see, how that works either when we do or don't do it in just a second. Probably the rest of these we don't hear a whole lot. Cardinality is one that you'll hear maybe DBAs use, in some cases anyway. The cardinality is a math term that worked its way in because it was math people that developed this stuff. It just means number of things. So if I ask, what's the cardinality of a table? What am I asking? How many rows does it have? Okay. How big is it? Okay, so the cardinality of a table means number of rows. But if I ask you, what's the cardinality of a column? What do you think that means? What's the cardinality of a column? I'll give you an easy one. What's the cardinality of the gender column? 2, right? There are 2 unique values in that column. We may have 100 million rows on the table, but the cardinality of that column is 2. That's important for the database to understand, actually. Because what if I come along and say select where gender equals female? If there's 100 million rows on the table, how many rows am I going after? 50%. Well, depends, right? The database will probably assume, given that we know at least that much about it, there are 2 values. The database will probably assume you're looking at half of them, right? There's 100 million rows, 2 values for gender. I said select where gender is equal to 1 of them. Database thinks, at least, that we're going after half the rows. How did it know that? Well, it knew, perhaps anyway, the cardinality of the gender column. How does it know the cardinality of the gender column? It's in statistics. And we'll talk about statistics a little bit more when we get into performance. Okay, but you'll hear that word start to creep up. You know, what's the cardinality of this column? And that has an awful lot to do with how the database is going to optimize a query. If it knows you're going after half the data, you know, is it more or less likely to use an index than if you're only going after 5% of the data? Less likely to use an index, right? Less likely. Particularly if the half the data that you're looking for is scattered throughout the table space, right? If it's random. What's the best way to get half the data from all of the pages or blocks in the database? Scan it, right? What's the best way to get all of the data from half of the blocks? Say that right? All of the data from half the blocks or half the data from all the blocks? All the data from half the blocks, we'd like an index to direct us to which half, right? But if I'm getting half the data from all the blocks, I'm probably going to see table scan. So sequential versus random comes into play there. And cardinality of the columns, right? So that the database can make at least an educated guess about how much data are we talking about. Cardinality is one of the things that you get when you get statistics on your tables. It'll look at just particularly your indexed columns, and maybe more if you ask it to. What's the cardinality or the number of values for that column? So if I say the cardinality is 100,000, and I go say out there and I say select where column is equal to a value, the database assumes, by default anyway, 1 out of 100,000 rows will qualify. Every 100,000 rows will qualify. It's a guess, but it's at least an educated guess, right? And that's going to be critical to the optimization of that query, an understanding of how much data are we talking about. Should I use an index or not use an index? How much data are we talking about? What order should I put the tables in the join sequence? If I join 5 tables together, which one should be first? Just generically speaking, which one should be first? The one that, yeah, it gets me down to the most narrow subset of data, right? How does it know that? Looking at things like cardinality. Okay. So we'll talk more about that as we get into especially access path analysis. And the second part of the week, probably beginning on Thursday, we'll do a little bit more in-depth study on access paths on the different platforms. And again, we'll focus on DD2 here just because that's what we have the tools to use, but the concepts at least are similar on all the platforms for optimization. We're talking about domain. Domain of a column is, the set of allowable values for that column. And then we can get the database to enforce for us as well. Tables at their core are not hard to understand, right? Here's a table. Tables have columns and rows. Kind of the important thing to understand in relational theory, and in relational theory there was only a table. Relational theory does not address things like indexes, does not address the physical structure of the way data should be stored on a disk. It just talks about tables. A table is really the only point of contact I have with at least ANSI standard SQL. You select from tables. Now, for you Oracle people, you can put little hints in there, right? With comments and say, hey, use this index, please. Okay. So there are extensions to SQL that allow you to mention other things, but ANSI standard SQL anyway. The only thing I ever talk about is columns on tables. That's it. Everything else is figured out by the database itself. And I care about it when I start caring about performance. Tables with columns and rows is really, you know, if you get that, you're 90% there on the rest of relational database theory anyway. And so a row is a set of values for all the columns. A column is an attribute or a thing we're keeping track of. And we generally start, when we're modeling data, we generally start by kind of identifying business objects, things I need to keep track of, and then what are the attributes of those things. We will then go through a process of normalization. And so one goal of managing this data this way is to try and maintain the integrity of the data. And when I'm trying to maintain the integrity of the data modeler will go through a series of steps to normalize that data. And I guess I can say that word now, so it's okay to say it. I'm told not too long ago that was a dirty word. Okay, so normalization, what's the goal? I mean, when you come, if I give you a database that's in first normal form, it might have 5 tables. If I take the same database and I take it to third normal form, we might have 25 tables or 100 tables. So what's the point of normalization? Which is easier to manage, a 5-table database or a 100-table database? Depends on what your goals are, I guess. That's why sometimes normalization gets that stigma to it, because it generates a lot of tables. The rules of normalization, and some of those are listed for you on the right side of the page there, right? So if a database is in first normal form, we take all the repeating fields and we move them to their own table. Right? So a great example of this, the first database that I worked on was a claims history database for an insurance environment. And they went through the normalization process to some extent. But one of the things they keep track of in a claims environment is, what procedures did the doctor perform? So you might go to the office visit and they diagnose you with 4 different things. That's 4 diagnosis codes. And then they do 5 different procedures on you. So that's 4 diagnosis codes and 5 procedures. What did we have on our table? Diagnosis code 1, diagnosis code 2, diagnosis code 3. I think we had up to 6 of them. Up to 6 different diagnoses they could put on you for a particular claim. And we had repeating columns. Diagnosis code 1, 2, 3, 4, 5, and 6. That broke first normal form. Okay? First normal form says we take those repeating things and we push them off to a different table. Why do we do that? What's the point of that? Just making another table? So, well, what if I need to actually do a query that says, find me all the people who had this particular diagnosis on this particular day? Well, then I got to do a select that says, select where diagnosis code 1 is equal to guy 4. Select where diagnosis 2 is equal to guy 4. If I have them in their own table, I can query them directly without a bunch of ORs. How do I index diagnosis code if it's really 6? I have 6 different indexes. It's very, very difficult. So first normal form says we take all the repeating stuff, we split it onto its own table for flexibility. What am I going to have to do now, though? I have to join those 2 tables together when I need that information together. So we've created a join, probably. Every one of these steps of normalization creates the need for more joins in the application. But they're trying to work out anomalies in the data. And that's really what normalization is about. It's about working out anomalies. If you talk to the purists in this area, they'll say, when a data modeler does this, they should have no thought for performance. Right? They're working out anomalies. They're following a series of rules to get rid of anomalies in the data. And then when we get to third normal form, then the DBA starts maybe working backwards a little bit for performance. You might say, 100 tables is too many. I got to fold some of these back together somehow, because I can't do a 100-table join. I don't want to anyway. Okay. So we might back off of some of this normalization for performance reasons. But at least the purists, the academics in this world will say, data modelers shouldn't be thinking about performance. They're thinking about applying business rules and working the anomalies out of the data. So, yeah, go ahead.
Just so some people know, Pega works, we actually did this. Because the way our product currently is with that blob, we had that in our older C++ version of the code, which was built off originally the CSCS VCNF version.
Right.
So we had these, everything was a blob pretty much. And Alan wanted customers to be able to use third-party data warehouse products to actually examine the data, but we had everything in our own format. So we had this thing called Open Folder, which was to normalize all those repeating lists into child tables and so forth. And then we actually, what we did was we actually had stored procedures that did all the joining. So the engine layer saw it as the same thing. They said, oh, just read this record. And then the stored procedure knew all the,
map it back to,
how to map it back to the blob, read it in all the separate columns and read the repeating rows, and then return it to you. And of course, it was slower.
Yeah, exactly.
So slower. Even though someone argued it would be faster.
Right, and you could probably have predicted that to begin with, right?
Alan did. Sorry.
Right. So why would I use a fully normalized relational database versus a more optimized, flatter structure of the same data that's optimized for a particular application? We'll go with flexibility. Yeah. So we can still get these things to perform pretty well usually, but it's not going to perform as well as something that's optimized for a particular application that's going to use it, right? In other words, you put something over here and you're going to go back tomorrow and get it, and it's going to look at the same form. That's going to be a fairly optimized operation. But putting something over here when it's a relational thing, you might have to map to 5 or 6 or 7 or 8 different tables. Right, and that operation is going to be slower than just sticking it in a blob or a blob-like place. But we do it for flexibility and functionality that we wouldn't otherwise have. Right? So it's a trade-off. Can we do that and still get acceptable performance, if not, lightning fast performance that we might expect from a more singular focus on a particular application. That's one of the goals of normalization and relational databases in general is portability, right? Allowing this data to be used for more than one thing. And that's why we would do it. So you see second normal form, what do we do? Move things that are dependent on only part of the key. That's third normal form. Look for anything that is dependent on some stuff that's not in the primary key. So great example of third normal ways we break third normal form all the time is address data. You guys have that in your application anywhere you store addresses? Well, you can get a great debate going about how to do that, right? What's the best way? What's the most relationally correct way to do it, and what's the most practical way to do it? But what's one thing that's in the address that everything else in the address is at least partially dependent on? The name of the person? How about zip code? Right? The city and state dependent on zip code? Yes. So third normal form says, well, we would take those out of that table and put it in a zip code table. Right? So Cambridge, Massachusetts, what's the zip code here? 2412. Right. So if I tell you the zip code is 02412, I don't have to tell you city and state. Right? Those should be different tables according to third normal form. Right. Do we actually do that? No. Right. So that's an example of things in the table that are dependent on something other than the primary key of that table. Right? If this is a table about person, person address, let's say the table is called person address. What's the key to that table? Person number or customer number, whatever you're calling it, plus whatever else makes that thing unique. And zip code, or city and state are dependent on zip code, not the person. So third normal form says we break that all down. We have probably 3 or 4 different tables for normalizing the address situation. And what do we usually do? We say no, that's all going in one table with the rest of the address.
Well, the other thing is, in that sort of situation, if you had a zip code table, you'd still have to have foreign key to the zip code table anyway.
That's right.
Which would be the zip code itself,
right.
Which is kind of a redundancy.
Right. You would still hold the zip code, which would be a foreign key. But if you were relationally correct, you wouldn't say city and state. in the address table itself, that would be off on a zip code lookup table, right?
Yeah.
But we don't do that usually. We back off of third normal form a little bit there, just for practical purposes. I'm not really worried about redundancy in the city name, right?
Yeah, I suspect the big difference there and why that's kind of a one-off type situation is because you don't expect a zip code to all of a sudden the state or city or state to change on it.
That's
Whereas
right.
with that same exact thing where it was, if that was something where city and state changed zip codes, you'd only have to update it one place, and everyone who had that key would still be in the right. They're going to change the name of city's frequency.
Right.
Instead of reading everyone's record and changing this thing that was dependent on something you had a key to.
That is the goal of normalization, right? Is to get rid of those anomalies. When a piece of information changes, how many places do I want to have to go change it? One. So in our theoretical zip code application, if the zip code for this office changed, which you'd be surprised actually how much that does happen. I worked in a really address-intensive application, and the post office is all the time sending out updates to, hey, we created these 100 new zip codes, and it's for areas generally where the population is growing and the dynamics are changing. Okay. It happens more than you would think, but it's a relatively static operation, right? But if the zip code for this building changed and all the buildings around it, we could go one place and change it rather than dozens of places if we fully normalize the table out.
I remember one woman at a database conference talking about how she thought VCNF was the greatest thing since sliced bread.
Which is a little bit more restricted
more refined third normal form. And I looked at her examples and I said, I still want to print out address labels.
That's right. And now I've got to join.
Yeah, and now you put a whole bunch of things together, and I can't get my address labels the way I want them. It just seems silly.
Right. So the academic's perspective on this is, and there is a VCNF, voice card normal form. Basically, they came up with 5 normal forms: first, second, third, fourth, and fifth. And then voice and cod came back and said there's really one between third and fourth, so they called it voice cod normal form. The general consensus out there is we go to third normal form, and that's where we stop. And then DBAs might back off of third normal form in situations where we know it's going to be a performance problem. Like if I have a very common operation to do that's going to now take a 6-table join to accomplish, we might back off of third normal form a little bit, introduce some redundancy back into the system, with the understanding that we need to do that for performance. So the main reason we back off of third normal form is for performance. In my mind, the data modeler should have at least a passing thought to this before they go to third normal forming. That things like the zip code address situation, if they blindly go to third normal form with that, then we're going to end up backing, they're going to end up creating structures that we know we're going to back off. So, I don't think this should be done entirely in isolation of performance, but it makes sense to kind of have that discussion with the data modeler and with the DBA and with people who actually have to write the queries that run against this stuff. Okay, so third normal form is what we've discussed here. There is a fourth and a fifth. Things that are in fourth and fifth normal form, they're generally they're real interesting situations that just don't occur very much in nature anyway. But, third normal form is generally where it's generally accepted where the data modeler should leave off, and then we can back off of that for performance consideration or practical considerations. Like how do I print an address label if the address is scattered all over the place? Okay. They're difficult. So the very first system that I actively modeled, I was still living in academic land at that point, and I had addresses off. I wanted addresses to be reusable in my system because it was actually a medical provider directory. So the physician could practice at more than one location. And so I wanted the address to be ultimately reusable. I had an address table with nothing else but the address on it. And then we linked to it, with warranties all over the place. we ended up denormalizing all that and pulling all those addresses back to the place that they were actually going to be accessed to cut down on some three-table joins that were going to have to happen really, really often. Okay. So there's an academic way to look at this, and there's a practical way to look at it. Experience has taught me that practical has to win out, but you don't want to lose the purpose behind normalization either, which is to get rid of the anomalies, to eliminate duplication, to make things queryable. First order form is all about making things queryable that would be really difficult. If I have 100 different occurrences of something, I don't want 100 different columns on the table and have to query each one then to see if a particular value exists somewhere there. Put that in its own table. Okay. Any other thoughts on normalization? It was frowned upon, now it's being talked about here, I guess. You got it. So somebody give me a little bit of background on how this is coming into play here. The way I understand it is you're starting to pull some things out of those blobs for reporting purposes. So that
we have to basically we use SQL to get at data. So we wind up with various mechanisms to pull stuff out of the blob and call externalize properties
onto the more relational tables.
And once it's externalized, then we can back write queries, write reports, and stuff.
I think there's some initiative going on currently right now for the current product. I don't know if Jamie would be the only one. I think that you know anything about that or what Emil is talking about.
I think now, yeah, I mean, I know there was some stuff that with Emil having to talking about basically taking anything in the blob and making it queryable. But we have, even with the new reporting facility, we aren't there yet. We're still just doing straight SQL. And it's what we've done really in the new reporting facility is we've made the whole definition of reports easier for people.
So you use store procedures sometimes to kind of put a layer between that? Okay,
We either know if it's exposed, we do keep table structure information so that when we generate, so if someone creates a report, we know which fields are able to be put in a where clause without causing major performance because those are the exposed ones. And nowadays we don't really allow them to.
They gotta have something that's exposed.
We've deprecated those things that allow them to put values in the where clause that are in the blob because you're doing a table scan, reading the blob, then doing a comparison, a mess.
But you've also exposed more things, it sounds like, that are easily searchable.
Actually, we keep distinct units, everything's contained within a table. It's not necessarily any foreign keys or anything in our system right now.
Thanks for that. It's, like I said, the more I can understand about the way things work here, the more we'll try and tailor the rest of the course to that.
Basically, everything that's exposed, sorry, just so you know what the blob really is, so it's compressed in our own internal format. Everything that's exposed is actually in the blob. If you update something external, it won't, it's not actually really. So if an external SQL statement came in and just updated a column, it wouldn't actually get updated. So if you actually read back that record, we just ignore all the columns, we just read the blob, uncompressed, and there's that's the real record. Those are just there for read, not for
read access.
Yeah.
And so they shouldn't be updated apart from the application also updating the blob.
You have to update the blob.
Right.
Anytime you do things that you decide, I really want to update this thing, you read it back with a lock on the blob.
Right.
You update the blob.
Update the whole thing. Yeah. Okay. Interesting. And what's in the blob is really just an externalization of the class or the object.
Correct. But it's got repeating.
Right.
It's
flattened out, right?
Right. I mean, basically, you think
it's an XML. Okay.
You think of it as our primary data as work objects, which are really documents.
Right.
So the documents tend to have a hierarchical structure.
Which is XML. Right?
Which is XML, which is why XML was a nice fit.
Yeah.
For this. But you know, if I've got, you know, contract or something like that, you know, who's involved in the contract, or the terms of the contract, or the terms might very well be a repeating group.
Sure.
And so forth. So, but fundamentally, we deal with the electronic equivalent of documents,
Right.
which is why this stuff is all, and you know, you want to have a document all in one place.
Right.
It's just that if you want to query stuff, it's not going to be a convenient way of doing it.
Exactly. Okay, that makes sense. So the later releases of all these databases in with DB2 was later to the party. We just in version 9 versions of DB2, they allow you to store XML directly, right? So does Oracle and SQL Server. Has that been looked at, or is that?
Yes, it has been looked at.
Yeah, because then you do get more ability to query into that document directly, or more directly. And I played around
Does
that.
DBC support looking into XML or not?
Yes. JDBC?
Yeah.
Yes. Okay, I believe so.
Yes, it's not
No.
correct.
Yeah.
Okay.
But one of the nice things about it, and I actually experimented with this a little bit, you can actually, if you have an XML column and you just stuff it with a big document, you can actually create a view over that flips it on its side and makes it relational and look relational. So that some people can look at it as XML, you know, your application can look at it as XML, but another user could come in and write a query. Now, tuning that for performance is a whole other interesting topic. You have to get into XML indexing and all that. It's a kind of a way to, the goal, and all the database vendors are trying to get there. The goal is to be able to take a set of data and store it as XML or store it as relational and look at it either way. All right, that's the goal. And I think they're getting fairly close. So if I'm storing things relationally, one of the ways that the database allows me to protect the integrity of that data is by establishing a domain. This is called domain integrity. Okay, so there are an allowable set of values for every column. And part of that is defined by the data type. And we'll look at, in the next chapter, data types as they are implemented in each of the three vendors that we're going to talk about. So we're focusing on DB2 and Oracle and a little bit of SQL Server. Do you guys support any other platforms? Do you see any Sybase floating around? Or?
Well, we allow strong connections to other databases.
Right.
Or
Okay.
Sybase. Okay, strong connections, so whatever DB support, we support.
Right.
We don't run into any specific platforms.
Okay, got it. So MySQL and
Yeah, that would carry. Okay.
yeah, got it. Okay, yeah, and then the stuff in this book is really tailored towards the big three, which is what you guys support. Okay, so one of the things that makes up the domain is a data type, right? What kind of data can go in? Is it character data, numeric data? And that is actually a fairly significant area of difference between the platforms. I continue to be surprised at how differently the different platforms deal with things like dates. Oracle, again, being the one that deals with it very differently than the other two. But you take a column like the gender here, right? We could say, okay, it's char 1, character 1. Is that completely define the domain of that column? Probably not, right? We really have two allowable values there, where char 1 says any acceptable character. We can, in each of these databases, further define the domain if we want to. We can say, okay, the gender code can only be an M or an F. Now, as a practical matter, I don't see a lot of places doing that, going further than the data type. But we can. There's things called table check constraints, which is a business rule that we can put on the column itself and say, okay, this column only allows these two values, or whatever set of values that we want. PBAs aren't particularly thrilled about those things because that means when the business rule changes, they got to go change the database rather than changing code. The gender may not be a good example of that. That business rule probably isn't going to change. you know, if I had a set of allowable department numbers, you know, every time we add a new department, we might have the DBA go make a change to the database. Probably not. So we don't see those implemented very much, but we can go beyond the data type and have a more restrictive view of what's going on or what's allowed to go on in the column. So the question of what is a database is a real interesting one. And it's something that physically varies by platform. So if you talk about what is a database in the Oracle world versus what is a database in the SQL Server or DB2 world, or what's a database even between DB2 on Linux, Unix, Windows, and DB2 on mainframe. Let's just say for now, logically, a database is a collection of tables that belong together. A group of tables that belong together. Now, in Oracle, if you talk about a database, they're talking about the actual physical files, really a set of files that hold the data. You know, that all goes together. And you can have one database mounted in an instance. You know, an instance for Oracle is more like the memory and the control files associated with the product. On SQL Server, we can have an instance of SQL Server and then multiple databases in there, but the data can't really talk to each other between databases, not easily anyway. DB2 on the mainframe anyway, I can have multiple databases and they can all kind of share and talk to each other and it's not a big deal. So the concept of what is a database physically is really dependent on the platform we're talking about. What is a database logically? A group of tables that go together. Okay. So we might have a database for an application. A collection of tables that have to go together. They can be queried together and joined together and all that. And so a database contains many relations or tables. Each table has attributes. Each attribute has a domain. Scalar value. Well, scalar value is just a term for a piece of data. So again, it comes out of mathematical theory, right? What's a scalar value in math? A number, right? A thing. Scalar value in database is a piece of data. Okay, so you can think of that as one column, one row. Right, is the scalar value of data. One of the strengths of the relational model is the ability to recognize that data in different places might be related. And that's really, you know, the term relational database really captures that that definition very well. And so we'll talk about referential integrity here just a little bit. We'll talk about how we can implement that in the database with the understanding that you guys don't do that here, at least not right now. The relational theory allows us to recognize relationships between tables. So here's a simple example, right? We have employees who work in departments. And who is the manager of a department? Well, that's probably an employee, right? So we'll have two separate tables here, an employee table and a department table. The employee table has one row for every person that works there. Department table has one row for every department. If we actually have, in these two tables, two different relationships. We have an employee manages a department, right? That's what we'll call a one-to-one relationship. One employee manages, an employee manages only one department, a department has only one manager. That's a business rule. Business rule might be different than that. But if we can recognize that in our relationship that we define, you know, this is a one-to-one relationship. We can also have one-to-many relationships. The department has many people working there. Right? One department has lots of people. You can't work in more than one department at the same time, but a department can have many people working there. These two are very easy to develop with relational database technology, one-to-ones and one-to-manys. A little bit harder is these many-to-manys. Many-to-many relationships, I've got employees working on projects. I can be working on lots of projects. A project can have lots of people working on it. It's a many-to-many relationship. Those are a little bit harder to implement, and we can't actually implement them directly. Well, we're going to need a third table an intersection table to associate. What we do is we break it down into two one-to-many relationships. See how that works in just a second. But it's all done with the keys of the data. Not internal pointers. If you're familiar with hierarchical databases like IMS or IDMS, that's all managed by underlying pointers. In a relational database, we manage the relationships with the data, with keys to that data. So we identify primary keys. A primary key is a column or group of columns that will uniquely identify a row. So on our department table, we establish the department number as the primary key. And we will also need a unique index on that primary key. Most of the databases will automatically generate the unique index for a primary key when you define it. The notable exception being D2 on the mainframe. You have to explicitly create it. The unique index is what really actually supports uniqueness. It's a special kind of index, there's no duplication at all. So if I go out and look for department C01, I should find only one row. Just stretch that. So if I look for department C01, I find only one row. If I try and put another C01 on the department table, I'm going to get an error from the database. You violated your primary key. When I take that primary key and I put it on a second table, on another table, we'll call it down here a foreign key. It's the primary key of another table. And this is the only data that I should duplicate between the two tables. I shouldn't take any of the other columns from up here and put them down here. If I do that, then I'm breaking first normal form again, right? Nothing duplicated. That's second normal form, actually. When I've done that, I've established this relationship, a business relationship between these two tables using the business keys to that data. Now, I don't have to tell the database that I did this. Right? I can just simply put this column down here and start using it this way. I can join the two tables together without telling the database that this is really a foreign key. I can optionally tell the database that this is a foreign key, and then what have I done? Kind of asking the database, hey, please manage this relationship for me, or help me manage it. So if I define this foreign key to the database, and I go out and I insert a new employee number 71, David Simpson, foreign key, department C99, what am I going to get?
Well, here you might not get anything. If that's a complete listing of departments, then lo and behold, you have an error.
Right, I get an error, right? Because, well, assuming this is a complete list of my departments, there is no department C99, so that's an illogical condition, right? Every foreign key value should have a matching primary key value up on the parent table. This is a parent-child relationship. This is a one-to-many relationship. We took the primary key of the table with one, we put it on the table with many. That establishes the relationship. If I tell the database about that relationship, it will try and enforce the rules of the relationship. Meaning, I don't have any orphan rows. Right? If I update John Geyer, doesn't work in department E01 anymore, he works in department B11. B11 really ought to be a valid department number, right? So if I update the foreign key, that's usually allowed, but I got to update it to something else that actually exists. Yes, sir?
Okay, if I go back to the previous slide where you define your relationships,
Yeah.
it looks to me, if I've got one-to-one relationships, that would probably be a good candidate to simply slam the two tables together.
Yeah, if I have a one-to-one relationship, over here, look, here's our one-to-one relationship. And this one's on page 1-26. If I have a one-to-one relationship, shouldn't I just put the two tables together? Okay, in a lot of cases you can. In this case, I would not, because I also have another relationship going on, right? Well, in this case, the two tables are actually related in more than one way. I got employees working in departments, I got managers of departments.
Yeah, but the fact is, if I might have a manager, you know, if I have managers, then I can still say, well, okay, that's an optional deal.
That's right. You could have like all of the manager information off to the right there.
And if I don't happen to have a manager, fine. If I not, if I don't, well, then I need to in fact assign a manager to that, presumably. But in the short term, it's still an allowable condition.
So I'll put an asterisk by your comment and say, if the only relationship between the two tables is a one-to-one, then it's a good candidate for rolling them together.
Yeah.
Okay. The only reason I wouldn't is because, you know, I'm basically taking two things that are
Yeah,
separate.
if you're taking all your employees, obviously,
Yeah.
then you have a one-to-many.
Right.
But if I'm just taking, if I only have managers, then managers and
Roll them together.
roll them together.
And I don't think you're even breaking too much in the way of normalization rules by doing that.
I would think that would be pretty clean on normalization.
Right. Because these two tables are related a couple of different ways, though, it makes sense not to store all the manager information up here because it's got to be down here too.
Yeah.
Right.
So manager is an
The
employee.
manager is an employee.
Yeah.
Right. The manager is an employee.
Supplies.
Any managers in here? All right. Check out that manager for D01. Null. So null is a special value. We'll talk about it in chapter 2 a little bit more. But when I establish, if I tell the database about this relationship, I've got to have a way to say there isn't one. Right? D01 does not currently have a manager. I can't put spaces in there if I've told the database about this relationship anyway. There is no person that has a primary key of spaces. Right?
Yeah.
I can't put all nines or high values or low values or whatever we would normally put in there. So the null value is a special value, and it's a little bit different. In Java, when you talk about a null, what do you mean? You mean like hex 00, right? I'm not a Java person per se. You have the concept of null, right, in Java? I think we're talking about something a little different here. The null value is really not a value at all. Right? It's an empty string, and it's not an empty string. It's not like spaces. It's empty in the sense that it does not exist. Right? We'll talk a little bit more about it in a second, but that can become important in relationships because you sometimes need a way to say there isn't one. All right, I don't have a value for this right now. So a one-to-one relationship, one-to-many, we always implement by taking the primary key of the one and putting it on the table, the many, as a foreign key. How do I do a one-to-one? Could do either way, right? Could go either way. So in this case, I've chosen to take the employee number and put it on the department table as a foreign key. Notice too that I've called the manager number here. It doesn't have to have the same column name in order to establish a relationship. Very often they do, not just for sanity, so that I know this is how I join the two tables together. I take the column names and the same. But it does not have to be the same name. I could have just as easily, though, taken the department number and put it down here. It says manages department, this employee manages department A00. One-to-ones, I could take the primary key of either one and put it on the other. Kind of want to do what makes sense for the business there, makes it the most understandable. But as an implementation, it could go either way, to one-to-one. How about many-to-many? This is that employee project. Many employees can work on many projects. I have to actually decompose that into a third table. And the third table is what we call an intersection table that has the primary keys of both of the other tables on. So look at employee number 10 works on 3 projects. Right? Project MA 2100 is worked on by at least 2 employees there. And it's the only way to easily represent this without having repeating fields, which we're not supposed to do in relational theory, right? So you have a row here that represents an employee working on a project, and to get all this information together, you might have to join 3 tables together at once. So many-to-manys aren't directly represented in relational theory. We got to break it into two one-to-manys to get it to work. Any thoughts on any of that? All right, so these are the big three. We've been talking about them already. There are others, right? There are other relational databases out there. We talked Sybase was used to be a big player. It still is in some financial institution, particularly on stock exchange. SQL Server from Microsoft actually was a joint venture with Sybase a long time ago, and like a lot of joint ventures that Microsoft started out in, there was a nasty divorce at some point. They each took the code and went their own way. So actually, Sybase used to call their product Sybase SQL Server, and they changed the name after the divorce. Okay. DB2 actually has two unique flavors, at least two. There's some other less popular ones, but you've got the Linux, Unix, and Windows version. So whether you go put DB2 on Linux or DB2 on Windows, they're actually operating from the same code base, even though they're different platforms. So you get similar behavior, nearly identical behavior from DB2 on Linux or Unix or Windows. DB2 on a mainframe is a totally different thing. It does not share the same code base as the Linux, Unix, Windows flavor of DB2. So just because you crack the nut on DB2 LUW doesn't mean the same SQL will necessarily work on the mainframe. From a SQL perspective, they're very close. And so the SQL that you're allowed to write on one platform versus the other is pretty close, but the way they optimize and deal with queries internally can be very different.
The COS version of DB2, is that still reflects more of the batch heritage of the mainframe?
Okay, so does DB2 on the mainframe still kind of reflect batch heritage? In some ways it does, but also I'd say a lot of the world's transactional systems now operate on DB2 COS. It's become a very solid transactional platform, which is interesting because its roots were more, I mean, back in the early 90s, late 80s, people said, never run transactions on that, that's for reporting. Right, that's for batch reporting. They're actually coming back around now trying to market that as a data warehouse kind of platform as well. Typically in the DB2 world, this is not 100% true, but typically you've seen more implementations of data warehouse and reporting systems on DB2 LEWs, and DB2 MZ has been more transactional lately. And they're trying to port the wisdom from both of those into the other. But DB2 LEW is actually a very powerful warehouse engine. And that's the idea being that these data warehouse reporting kind of queries consume a lot of cycles, and those cycles are cheaper off the mainframe than on the mainframe. Is a good cover, I think.
Specifically, DB2 ZOS2.
Yeah, we can talk about that as much as you want. So that's probably one of my favorite things to talk about is DB2 ZOS2. All right, so yes, we can talk about that as much as you want. If I talk about it too much, stop me and tell me to talk about something else. But yes, absolutely. So it sounds like that's an area of interest right now. Right? Just something to think about. Yeah. That's how you know it. Yeah. Well, IMS is a whole other animal. It's a hierarchical database. It runs on ZOS. Yeah. It's pre-relational. Pre-relational. Yeah. Hierarchical structure where you're chasing down a chain of data from the top. Yeah, I mean, it's not relational, so it's a wholly different thing. But it deals with XML very well because it's hierarchical, right? So I actually talked to one of the guys that writes IMS code out, that writes for IBM, writes IMS, and he said they came to him years ago and like, can we put XML? Can we integrate XML into the IMS database? No problem. Easy. Getting that into DB2 DB2 was a lot harder, in relational because it's a whole different model for modeling data.
I think IFS was created for the space program when they had there's a huge bill of materials problem.
Yeah. That's a little bit harder to solve with relational, isn't it? Yeah. Right.
All came from databases that are implementing variant records and batch systems.
Yeah. So yeah, so the original question was DB2 on AIX. AIX is one of the flavors of Unix, right? That Hygiene certainly supports. It's their flavor of Unix. So yeah, you got AIX, you got HP Unix, you got Sun, which now Oracle, right? And Linux. Linux is kind of probably where I see a lot of installations going now because it's cheaper, freer. SQL Server, surprisingly, only runs on Linux. Maybe that's not so surprising after all. So Oracle, usually, most of the Oracle installations I run into are Unix. They run on Windows too. They actually run on the mainframe, kind of. I've got one big customer that runs Oracle on their mainframe, which is very interesting. Wasn't really built or optimized for that platform, but they compiled the code and it worked, so they're right up there. Any other thoughts on that? Each of these platforms uses SQL. So we can break SQL down into at least 3 categories. The stuff that you guys are probably most interested in is down here at the bottom, data manipulation language. Select, insert, update, delete. I'll add 2 more statements to that, merge and truncate. And I think they're supported by all the platforms now. That's working with the data itself. Right? Select, read data, insert, add data, update, change, later, delete, remove. When you create and work with the structure of tables, create, alter, and drop, those are also SQL statements. So you can run those in the same query tools that you use to select data. And when the DBAs do that stuff, all they're doing is running SQL statements. So, easiest SQL statement in the world to write, drop table, give it the name, table gone. Right? Might be a little bit difficult to recover from that, but it's a 3-word statement, and it's just an SQL statement. If you're allowed to do it, you do it in the same query tool that you write a selected. Data control language is actually lots of kind of obscure statements here. Probably the biggest 2 are grant and revoke. This is how DBAs and security people control who can do what. And those, again, are just SQL statements. So they grant select access on the table to public. Everybody can read it. In the world of authority, all these databases work on the assumption that you can't do anything. That anyone who's not the owner of an object can't do anything to it unless they're granted authority. So it's kind of the opposite of some other security models where you can do anything you want until somebody locks it down, somebody takes away authority. With databases, you can't do anything until somebody says you can't. Either you own the object or somebody has granted you access to that object. Okay, but all that stuff is just SQL. Creating, altering, dropping tables is just examples of SQL statements. So here's a little bit of DBA stuff. Right? Create a table, and give it a name called depth. They're doing here a primary key of depth now. Now down here, they're also creating a second table called M, employee table. They're giving it a primary key, but they're also establishing that relationship. Now this is what you don't do, right? This is what you guys don't do here. Establish that foreign key. This is not required at all. So I can, even if I leave off this foreign key definition, I can still join these 2 tables together. I can still do everything I need to from a business perspective. But when I tell the database about that relationship, I'm saying, hey database, take charge of that relationship and make sure that it's not violated, that the rules aren't violated. Meaning anytime I start a new employee, the depth node that I put here had better match a depth node up there. Even more fun, what happens when I delete a department? this clause right here has made this table a child of this one. If I say go delete department A00, what should happen?
Either it should be prevented,
Yeah.
or you cascade your deletes.
Either I prevent it, or I cascade. There's actually a third option called set null, which just says null out any foreign keys that are equal to that value down here. Okay, but I gotta somehow maintain that relationship. I can't forfeit rows down here by deleting them up there. And there's actually an extension to this clause that we're not showing here that where I can specify what that delete rule should be. Do I cascade? That's the most fun, right? You delete one row here, you might lose lots of rows down here. Great thing about that is none of the three implementations or vendors tell you when that happens. So you cascade a delete, it will come back and say one row deleted, and not tell you about the 100 rows that it deleted down here, or however many there are.
Oh, sweet.
It's useful if you wanted to reassign it to the department.
Right, if you want to reassign this, in this case, I would either implement a restricted delete, which says you can't delete this until you do something with the people, right? Or a set null delete, which says just take the people who are working that department and set their department to null, and we'll reassign them later. Okay. I wouldn't do a cascade delete with this relationship. However, there's been a lot of cases where I have done a cascade delete. It can actually be very useful for an application. You know, I have in my insurance environment, we had a table for contracts, like a subscriber, a person. And that person had claims, and those claims had line items, and those line items had diagnosis and procedure codes. So there was a chain of about 7 or 8 tables deep, you know, branched out actually too. If I want to delete the contract, you know, they canceled their contract with us, it's been 5 years, you know, I don't need to remember anything about that person anymore legally. All I had to do was go delete the contract from the contract table, and everything else about it cascaded down all the way down. Okay. So if I was a restricted delete, I would have had to start from the bottom and work up, go through every table, every layer, and do it in the right order. But with the cascaded delete, I just issued one delete. Should I be careful with that? Yes. If you're implementing cascaded deletes, you want everyone to know and understand what they're working with, and that one row deleted here is not one row deleted necessarily, but maybe many rows from other tables. It's a business rule. It's you know, what do I want to happen from a business perspective when I establish that relationship? Again, if you don't establish a relationship, it doesn't mean I can't work with these two tables together. I can still join them together, but the database doesn't care whether I work from the rows or not. I have to manage that with code. And that's a valid choice. It's a valid option. I'd say probably half the shops I visit do not implement declarative, this is sometimes called declarative referential integrity, or system managed referential integrity. About half of them do, half of them don't. There's some horror stories in the old days about performance problems with declarative referential integrity. I think most of those happen when you don't have things indexed the way they need to be for that to work. Database never makes me index a foreign key. I probably almost always want an index on the foreign key, but it doesn't force it. And if you forget to do that, then you got issues, right? After when I delete a department, it's got to go look to see if there are any of those people. No index. So every delete is a table space scan down here. Okay, so got to be something to be careful with. All right, the next stuff we'll probably cover fairly quickly. It's kind of the basics of, this is what Dr. Todd prescribed back in the 60s for, this is before any relational database actually existed, but he said, you know, anybody who decides to do this really ought to provide for all of this stuff. You know, a restriction, a projection, a join, negative intersection difference, product, and divide. The divide is the one that never really actually went back and implemented with SQL. We'll actually look at how you do that later, but that's a kind of a special case. So, restricting rows, you know, the idea that I don't have to process the whole table. That's a good one, right? I can actually randomly access this thing. So, in this case, I only want the people who work in departments that begin with the letter D So I have a couple of D01s and a D21, or this, I'm sorry, only departments that begin with the letter D. D01, D11, and D21. I can easily produce a result that only has those rows in it. And so that's, in academic terms, called a restrict. A project is only showing me the columns that I want. So this table I got is like 5 columns on it. I only care about 2. I only select the 2 columns that I want. Can do both. Only show me these 2 columns for the people who work in D, or for the departments that begin with D. So I can combine the 2 operations. And so relational theory didn't really prescribe the SQL language per se. It kind of envisioned a language that would have these operations in it. And then SQL was developed later based on kind of these specifications. The join operation. Dr. Codd said we should allow for joining 2 tables together. And the neat thing about SQL, and this join operation as they wrote it up even back then, is that SQL always produces a table, right? A select table, always produces a table. It could have many tables as input, but the output of a select statement is always a table, columns and rows. That's a pretty powerful concept, actually, because what that means is the output of a select statement could be the input to a select statement. What's the input? Tables with columns and rows. What's the output? A table with columns and rows. I can build select statements on top of select statements, kind of stepwise. Very powerful. So here I've got a situation where I got the department table and a project table. Project table has a department that's responsible for it as a foreign key. Now I want to find a result containing the project number and project name from the project table along with the department number and name of the responsible department. So I should be able to produce a result that looks like this. And if I join these 2 tables together, this is what I'll get out, is a table. The columns on my result table here are mixed, right? I have a couple of columns from the project table, I have a couple of columns from the department table, but I get out a single table with columns and rows from both of the other tables. And we're going to use those primary foreign key relationships to establish the match between the 2 tables. All right, I'm going to spend a good part of tomorrow doing joins. We're going to talk about joins. And I got what I think is a fairly robust workshop on joins, and we'll talk about some of the contributors to join performance, especially because join is one of these operations in relational databases that's kind of expensive still. We're taking data from physically separate places and trying to put them back together. So we'll talk about that. We'll spend a good bit of time on that tomorrow. So we talked about the components of the relational database already a little bit. The last one we want to focus on here is the optimizer. This is on page 1-48. Database optimizer. Again, this is that piece of code that figures out how to do SQL. It's built into the database engines. Figured out how to do SQL. This is the thing that's like the GPS navigation system in my car. When you submit a piece of SQL, a select statement, you've told the database what you want, but you haven't told it the first thing about how to go get it. So let's say you do a 5-table join. Not that unreasonable these days anymore. It wasn't that many years ago that at least on DB2, the maximum theoretical number of tables you could join together was 15. I always thought, well, that's plenty. Somebody in my shop tried to write a 16-table join, and it wasn't enough anymore to break it into 2 statements. Now, at least on DB2 now, the maximum is 225 tables in the join. I think the other platforms are very close to that. Very similar numbers there. So we don't do that. But let's say I join 5 tables together. Which one should be first? Which one should it access first? The one hopefully that narrows the result the most, maybe? Okay. Out of that first table, what index should we use? What if there were 2 or 3 possible indexes that could both narrow the result, that could all narrow the result for us? Which one should it use? I don't specify that stuff in my SQL unless I'm using hints. The optimizer is supposed to figure that out for me. It's not supposed to just pick any old way to get the data. It's supposed to pick the best way to get the data. And by best, we mean best performance. It does that based on what it knows about your data. So the optimizer, when these queries optimize, it doesn't really know what your data looks like. It knows the statistics. And so the DEA occasionally, or now sometimes, a lot of these database engines gather statistics more dynamically on the fly. But the statistics are, a process by which the database actually collects data about the metadata, or data about the data. You can tell how many rows are there, how many values are there for the different index columns. Puts those in the catalog. Okay. And then it uses them to make decisions about what's the best way to do things. So I got a couple of pretty decent examples of explains or access paths on each of the different platforms, and we'll look at those a little bit later in the week. At a high level, at the 100,000 foot level, I don't care about this. All right? I submit a query, and it figures out how to do it, and it does it. I start caring about this stuff when I start worrying about performance. Okay. So if the only SQL you do is select from the table where primary key column is equal to a value, you probably don't need to think about this a whole lot. It's really only about one right access path for that. Use the primary key index to go get the one row you're looking for. It's probably the access path you're going to get almost all the time. But if you have more complexity in your SQL, if you're starting to join tables together, then this stuff becomes a lot more interesting for performance reasons. Optimizers will always give me, unless there's a bug in the code, they will always give me the right answer. And so there may be 4 or 5 or 6 different ways to get the right answer. It's supposed to pick the one that's the least expensive, but that it perceives to be the least expensive, based on all the educated guesses it makes about my data. Okay. So I know I was talking about a query with me this morning that he says, when we run it on Oracle, we get sub-second response time. We run it on SQL Server, we get sub-second response time. We run it on DB2 for Linux, Unix, Windows, sub-second response time. DB2 for ZOS, what was it? 15 seconds? Okay. What's that? Oh, they get to look at it too. Okay, so maybe the result of this class is a fixed fit query. Hopefully, at least that. Okay, so what's wrong? Well, unless we lift the hood and look into this optimization, we don't know what's wrong. It got us the right answer. It took 15 seconds, but it got us the right answer. What are you complaining about, right? Well, the optimization is there's something in the optimization for that query on that platform that's very different about the way it is on all the other platforms. We got to figure out what that is. Right? Okay, so the optimizer is, when you submit an SQL, so you type an SQL statement, you punch the run button. This happens on the fly. Right? It optimizes it and then implements that plan. If you write stored procedures, particularly, when does this stuff happen? When you compile a procedure, when you prepare the procedure for execution. Yeah. That's an interesting difference, isn't it?
Well, that also means that if you've done other data manipulation, that you might very well wind up, if you were doing things on the fly, coming up with completely different decisions.
That's right. So, particularly on the mainframe, DB2 on the mainframe has a very long history of what we call static SQL, which is the way stored procedures work on all the platforms usually. If you write a COBOL program up on the mainframe and you compile it correct for execution, you come out of that with a BOM, a statically bound package that has the access path for the SQL you wrote already in it. Mainframe people have a long history of not ever rebinding that package unless they have to. Okay, so I was in one shop further up in New England a couple of years ago, actually, where I found packages that hadn't been bound since 1992. Why didn't you bound this? Because it didn't change. Right? Code didn't change, why should I rebind it? Well, there's been a little bit of technology since 1992 that, you might want the package to be aware of. But it came up with an access path in 1992, and they've been running it ever since. That's what that means. Okay. First, this is what happens with stored procedures on all the platforms. If you write SQL and put in a stored procedure, it's figuring out how to do that at the time you create the procedure, and it stays that way until something causes you to regenerate that stored procedure. There's some pluses and minuses to that, right? Number one, if it's static, I don't have to figure it out every time I run it. Okay. And number two, it's stable, and I don't have to worry about the access path changing to something worse because it's static. I came up with it, and I optimized it presumably, and it's going to stay that way until I recreate the procedure. What we typically have in your Java applications is dynamic SQL. Dynamic SQL, database doesn't know about the SQL until it shows up to run. So you do a prepare of a statement. This optimization happens at prepare time for dynamic SQL. Now you may prepare the statement and run it a bunch of times, so I'm going to optimize it once. And all of our databases now have caching of those access paths up in memory. So if the same statement comes in 20 times in a row, it'll optimize it once and then reuse the plan many times perhaps. Okay. But it's still more dynamic than this, which can last for years.
Is there any way across the platforms, or this platform specifically, could automatically say, okay, after so many days, rejigger this thing, reevaluate? No. So that would be a matter of coming up with a script or something to rebind or regenerate these things. Okay, so that's no DBA responsibility.
It's generally viewed as a DBA responsibility.
Okay.
On DB2 ZOS anyway, I like to recommend for my clients anyway, at least once per release, So if you're on DB2 version 8 right now, and you haven't bound since version 7, at least rebind once while you're on 8. Because you don't want to go 3 releases up and then find out you really had an access path problem back in version 6, but you didn't know about it because you didn't rebind your packages until version 9. So you want to do it once in a while, even if it's not strictly required. Okay, but there is something good a lot of times about the SQL being pre-thought and known to the database at the time you execute it. First of all, your DBAs can see it, right? They know it's there. Where with dynamic SQL, they see it when it shows up. And secondly, it's you're saving effort at runtime. Right? Pre-thinking the access path. You get some stability. So we'll talk stored procedures a little bit more later, but this is one key difference between stored procedures and running SQL directly out of your JDBC. Dynamic versus static. Pros and cons to that. Yes?
You say the dynamic that if I run the query multiple times, it only uses the previous one, like the star, every time it tries to come up with a new file.
Probably. Okay. So probably it will reuse it. The way the statement matching works is if your statement comes in exactly the same way every time, it's probably going to think the access path through once and then reuse it out of the cache in memory. Okay. Now, when you shut the database down, it's gone. Right? Again, it's going to have to rethink it again next time before the cache fills up. But yes, it will probably reuse it. And that gets to, do I use parameter markers for my variables or do I use literals? If you use literals, is it the same statement the next time? No. If I say select where employee number equals 5, and then the next time I say select where employee number equals 10, that's 2 different statements. If I say select where employee number equals parameter marker, then it's the same statement and it comes up with an access path that can be reused. There's some levers and knobs that DBAs have to tweak that stuff. But yes, in recent releases of all of these databases, there is caching of that dynamic SQL. So it's not a full prepare. It's not a full prepare every time. Can reuse those access paths. If you're in a stored procedure, though, it's fixed at the time it was compiled or prepared. Any other thoughts on that?